We talked in brief about physical layer. Now it is time to talk about data link layer. So data link layer, it is called data link layer. So first of all, I want to talk about MAC address. It is called media access control address. This is burnt in. Actually, MAC address is burnt in into NIC. NIC is network interface card. So it is called NIC. It has a MAC address. The MAC address is a 48-bit value. 48-bit value. It is too much to digest, huh? Okay, it is a 48-bit value, and we write it in hexadecimal. So how can I convert hexadecimal into bits? How can I convert bits into hexadecimal? Do I need to give you a crash course in hexadecimal and binary? Let's give it to you. I'm going to talk about 4 or 5 minutes about this. We have binary numbering. It has only 1, 0, and 1. This is the digits that are used in binary numbering. So this is binary. We have decimal numbering, and it has 10 different digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and these are the 10 digits, you see? And based on this, we can create different numbers. In binary, based on that, we can create different numbers. And we have hexadecimal numbering. And in hexadecimal numbering, we have 16. As you know, hexa is 6. So we have 16 different digits. And I want to write those just to be careful about the scheme that I am reading these. This is 0, this is 1, and this is 2. Be careful, be careful. This is 3. This is 4. We are reaching to the hard part. This is 5. This is 6. This is 7. This is 8. This is 9. And surprise, this is 10. And we have 11. We have 12. We have 13. We have 14. And we have 15. Oh my God. What are these numbers? We have 16 different values. So you do not read this A, B, C, D, E, F. You read this 10, 11, 12, 13, 14, 15. So we are talking hexadecimal in this format. And why would we go for hexadecimal? It is easier to write very, very big numbers in hexadecimal. And of course, it is kind of a binary. You see, this is 16 values. So it is dividable into 2. So MAC address is written in hexadecimal. How can I read this MAC address? And how can I read binary? And I want to talk about binary. Okay, let's go back to binary again. In binary, we can, define different values for a bit. For 1 digit, we have either 0 or 1. It has only 2 different values. So if I want to create numbers with 2 different bits, I can have 4 different values. You see, for these I can have 0, 0, I can have 0, 1, I can have 1, 0, and I can have 1, 1. So if I want to add more bits, I can define, more values with that. If I add, for example, 0, 0, 0, you can see that this is 3 bits. I can have 0, 1, 0, 1, 0, 0, 1, 1, 0, and this is one of them. And you can go and create 8 different combinations. So the number of bits is important. You can write the combinations or the possibilities. I want to write P for this, equals to 2 to the power of the number of bits. So if I have, for example, 4 bits, I can have 2 to the power of 4, and this gives me 16 values. So you see that I have 4 bits here, and with that 4 bit, I can define 16 different values, and these 16 different values are going to be my hexadecimal values. And how can I define them? I want to show you this. write 4 bits, for example x, 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 and these are 4 bits, and from right to left I give them values. The first value is going to be 1, the second value is going to be 2, the third value is going to be 4, and the fourth value is going to be 8. So these are the values of each bit, and because we are using just 4 bits, this is the values that we have. So if I start with giving zeros to all of these values, we are going to talk about the sum of these values. So if this bit is on, or if this bit is 1, actually on or 1 are the same here. If this bit is 1, it can have a value of 8. If this bit is on, it can have a value of 2. So you sum the values and you reach to 1 hexadecimal values. So 0, 0, 0, 0, all of them are off, so they have no value. That's going to be 0. And if I write 1, 0, 0, 0, you can see that the first bit has a value of, the first bit is on, so it has a value, and the value is going to be 1. The rest of the bits are not on, they are off. So I just plus 1, plus 0, plus 0, plus 0. This is the result, 1. What about this? I turn the first value off, but the second value is going to be on. The rest of the bits are going to be off again. So these do not have any value. This one can have a value, and the value is 2. You see, the value of the second bit is 2. So I sum the values. This is 0, this is 0, this is 0, and the only thing that has value is 1. So I have a value of 2. Now, what about this? 1, 1, 0, 0. The first value is on, and its value is 1. The first bit is on, and its value is 1. The second bit is on, and its value is 2. So I sum the values. It is 1 plus 2, and the rest are zeros. So it is going to be 3. You see that? It is very easy to work with this, and these are the conversions from binary to hexadecimal. Now I give you an example. Let me write this. I ask you, what is the hexadecimal of this? You see that this is 1, 1, 0, 0. I come and write the values on top of this. The first bit has a value of 1. The second bit has a value of 2. The third bit has a value of 4. And the fourth bit has a value of 8. You see that these two have no values, but these two have values. So I sum the values up. So the value is 4 plus 8. It is 12. And 12 is C. So this is equal to C. Let me give you another example. For example, they give you this value. They say 0, 1, 1, 1. And give me the equivalent in hexadecimal. So I go for this like this. I see that the first bit is on, so it has a value of 1. The second bit is on. The third bit is on. The fourth bit has no value, so this is not going to have anything. So 4 plus 2 plus 1, it comes as 7. Now, this is just a crash course. I didn't expect you to know this, and I do not expect you to learn this so fast. But this is what I am talking about. We are talking hexadecimal values. So when they give you a hexadecimal value, I'm going to back to my MAC address discussion. As I told you, this is 48 bits. 48 bits. I just want to select this. 48 bits. And for this 48 bits, if I divide this into 4-bit chunks, it is going to be about how many? It is about 12 by 4 bits. So it is going to be 12 hex numbers. So you can see hexadecimal numbers like this. This is, for example, one of the MAC addresses that you may encounter, 0000 dot 120A dot AB95. So you know that this is 0. This is one of the 4 bits. So is going to be 0000 in binary. The second one is 0000. The third one is the same. The fourth one is the same. This one is going to be, for example, 0001. This is going to be 0010, and like this. You see, each one of these hexadecimal values is 4 bits. Each one of these is 4 bits. So because this is going to be too long, we just write it with hexadecimal values. So in Cisco, we again come and put a dot between each 4 of them, but it is necessary. You know that this is just a separator. This is not necessary to be here. Because I want to read it easier, I just put the separator between each 4 of these hexadecimal values. So this is going to be one of the MAC addresses. So in next section, I want to talk about this MAC address more, because I want to tell you something that is so important about MAC address. Okay, that was really a crash course when talking about binary and hexadecimal conversion. Actually, I didn't give you a conversion back to binary. It is not important at this level. You do not need to know about this because you are not going to be tested on this. What I'm going to talk about is MAC address. You know that MAC address is a hexadecimal value and it has 48 bits. And this is supposed to be unique around the world. And actually, we know that for 48 bits, we have 2 to the power of 48 different combination. Let me see what the number is going to be. I guess it is going to be about, let me write it. We should go to programmer mode and type 2 and then click on, no, this is going to be in scientific mode actually. In scientific mode, we type 2 and select this one, x to the power of y, and type 48, and the number is going to be this much. Let me see this with separator. If I go here, and where's the message separator? Message separator, actually you should see something here about separation of this digits, or this is digit grouping. You see that it is about 281 billion, or more than this. This is not, no, this is too much. This is too much. You see that the number is too big, but not as big as we needed. Actually, we need more MAC addresses now. You know why? Because only one switch can have up to even 48 different ports. So one switch uses more than 48 of these, MAC addresses. So we may be in lack of MAC addresses soon. But what I am talking about is not, the low number of MAC addresses or too high number of MAC addresses. As I told you, this is supposed to be unique around the world. But I just go and conservatively say that this is supposed to be unique in your LAN. Okay, so why should it be unique in my LAN? And of course, it is not going to be, it doesn't have to be even unique in my LAN. It just has to be unique in my broadcast domain. And I am going to talk about a broadcast domain in a minute, because this is very important. But here, MAC address is the basic value, is the basic address to talk, to communicate, to find in my network. What do I mean by this? When I am on computer 1 and I am going to send a file, for example, to computer 2, and we are connected to each other. We are connected to each other using a medium, for example, a network, cable, whatever. I need to find out its MAC address, because I am going to put that on a frame header. By the way, what is frame? Frame is a unit of data. it is composed of a maximum of 1500 bytes. Is this the exact number? I heard something else. No, this is not the exact number. Actually, in Cisco networks, this is the number that we should know. Actually, it is going to be 1518 bytes. But we do not have anything to do with this 1518. We should know that there in Ethernet, and again, there is something else that you are going to be confused with. In Ethernet types of network, we are limited to 1500 bytes in one go. In one go, we put 1500 bytes on our medium. Our medium is going to be a cable, for example. So these 1500 bytes, some of them are the data that an application is going to send to the other device, but some of them are source address, destination address, source MAC address, destination MAC address, the type of data that we are sending, the checksum of this data that proves that this is not tampered and this is not, touched by anybody else, and a lot of other information. We have to send these information with a frame of data. And the frame of data, if I draw a frame of data like this, for example, this is the frame of data, and this frame of data has 48 bits for source MAC address, so I write it with SA. Oh, actually, this is going to be destination. The first one is destination address. And next, we have another 48 bits for source address. Then we have about 32 bits for destination IP address. I just write it as DI. We have another 32 bits for source IP address, and then we have type, and then we have other information about this frame, and then it starts the data. The bits for data goes here along a varying amount of data. I don't know how much it is going to be, and we are not just limited to 1500 bytes. Actually, we can create this frame with any size less than 1500, more than I guess 600. I guess something that's 618 bytes or something like this. I don't remember, or 618 bits or something. I just want to talk about this later because this is not important. The least amount of a frame, the least amount of the number of bits in a frame, it is not that important. Actually, we are supposed to know the maximum number of bits in a frame. And finally, we have about 4 bytes or 32 bits here. That is called cyclic redundancy check or checksum or something. This is a hashed value of the bits here, and this proves that this is not tampered, this is not changed, this is not damaged or things like this. So when I am going when I want to send a frame of data to another computer, for example, I need to know the destination address. I need to know this part so that I can fill this part of my frame with this information. And when I put the MAC address here and put it on the frame, the destination computer knows that this is related to me. I need to collect it from this wire, and I need to see and process the content of this frame. So this is why we need to know about MAC address. So what is the use of IP address? If we just need MAC address to send a frame from one device to another device, so why would we go for IP address? Actually, MAC address is not something that we work with. MAC address is valid only inside the broadcast domain. I'm going to talk about broadcast domain here. I'm going to talk about broadcast domain in the next section and tell you why don't we need IP address? And of course IP address is something that we can remember better than MAC address. And to my surprise, IP address is not going to be remembered that easy. Actually, we then go and translate that into a name. So you see that I am trying to reach, for example, server 1. What I need to do is to know this name. I send a query to something that is called DNS server. DNS server gives me an IP address. And again, this is what my computer needs. Again, when computer talks to the network interface card, it tells me that I do not need this IP address. Based on this, I should find something that is called MAC address. And when I know about the MAC address, I just send the frames to the MAC address. You see that this is a multiple step process to send the frame. We just go for MAC address in one broadcast domain. But we cannot memorize MAC address, so we go for IP address. IP address is something that our protocol stack needs to talk to. Again, this is not what we are interested in. We just want a name. The name is important for us, but this is, as I told you, a multiple step process to send the frame to the destination. So let me talk about broadcast domain in next section, and then I will talk about MAC address more.